in the multivariable case for detecting maxima and minima of function. So we are talking about finding maxima and minima. So all functions with the real value. And as usual, because we want to take derivatives, they are going to be defined on open set, let's say U in some R. So we want to study local maxima. So the question is, how do I find the candidate points and how do I tell whether the function has a maximum or minimum there? So we will call this candidate point E. How to detect if one occurs at some point A in the domain. So what is striking is that the argument in the real case, that is so the linear algebra, I've decided that we will just black box this linear algebra, but it is something that you have seen. So let me note it down. So we should also start recording.
Recording in progress.
Okay, so we will see the analog of the second derivative test for local maxima and minima that you have already seen last semester. And we need help of some linear algebra. So let me state precisely what we are doing. So linear algebra. So suppose I have a symmetric matrix. Let's say n by n. And you should immediately think of the situation in which we are going to encounter this. This is going to be the Hessian matrix of a function which has continuous second partial derivatives. By continuity of these derivatives, the matrix is going to be symmetric. All right. So what do we know about such a matrix? Then what do we know? Come on.
Its eigenvalues are real.
Yeah, say that again, please.
Its eigenvalues are real.
Its eigenvalues are all real. Moreover, the matrix can be diagonalized by means of an orthogonal matrix, right? So then there is an orthonormal basis BI consisting of eigenvectors. So I have already said that there is an orthonormal, first of all, a basis of eigenvectors. That means that the eigenvalues are all real. That is subsumed here. In particular, the eigenvalue, let's say lambda I of BI is real. But moreover, these VIs, they form an orthonormal. They form an orthonormal basis. So we have whatever the P A P inverse is equal to a diagonal matrix, but P inverse is equal to P transpose. All right. So a definition. So this is all right. So you should have seen this in the spectral theorem. And if necessary, we will come back to discuss this later, which is really just the proof of the spectral theorem. But right now, we will just take it for granted. So the definition, if all eigenvalues lambda I, remember they're all of A, symmetric matrix A are non-negative, then A is called positive semi-definite. If they are all positive, so there are various parts, they're all parallel definitions, then A is called positive definite. And likewise for the other side. So non-positive, that simply means less than or equal to 0. Then it is going to be called negative semi-definite. And if they're all strictly negative, then the matrix is going to be called negative definite. So note in particular that a symmetric matrix does not have to belong to any one of these categories, because we are saying that all eigenvalues must be uniformly of the same type. Okay, so it could happen that something is positive and something is negative. That is, there is a positive eigenvalue and a negative eigenvalue, in which case the matrix will not belong to any one of these types. Okay, so here is a sort of nice criterion, equivalent description of when a matrix is any one of these kinds. So I'll just write down one of them and the rest are parallel. So claim a symmetric matrix A is, let's say, positive semi definite if and only if for all non-zero vectors x in Rn, I have the following. Basically, I take the bilinear form defined by the matrix and evaluate it on the vectors x and x again. But we do not have to see that. So I'm just going to be concrete today. Everything is going to be in terms of matrices. So I have the following. X transpose AX is greater than 0, respectively greater than or equal to 0 in the semi-definite case. Okay, so let's try to prove this. Yes, is there a question? Okay, so let's see how this comes about. Uh, so if the matrix is positive definite, then how will I calculate this X transpose AX? So proof of the forward direction. So what do? I mean, I have a way of calculating this, right? I can, of course, what I can do is I can take the matrix entries and I can take the entries of the vector X with respect to the standard basis. But that is not using the information that is given to me. So of course, I should do this calculation with respect to the given eigenbasis. So let's do this. And the way to do this is I just write X as a linear combination of the eigenbasis Vi. So let's say Ci Vi summation over I. So let, and I just calculate. So what do I get then? Then X transpose AX is simply equal to summation, let's say I Ci Vi transpose A times, let's say, over J Cj, just to have a different index. And of course, what I'm going to do is I'm going to open, let's say, the second parenthesis and use the fact that Vj is an eigenvector of eigenvalue lambda I. And moreover, what do I know about lambda I? That it is strictly positive. Every lambda I is strictly positive. That is what is the hypothesis. So let's continue. So what happens? So let's say I leave the first parenthesis the way it is. Say Ci Vi, this vector transpose. But then the second one becomes summation over J lambda J Cj. Now what happens if I open the parenthesis? There are going to be n square terms, correct? However, only n are going to survive. And why is that?
The orthogonal property.
Right, exactly. So recall that Vi transpose Vj is simply delta Ij. So what do I get as a result? This simply becomes summation lambda I Ci square. And of course, all lambda i's are given to be positive to me. And Ci's, whatever they are, I'm summing their squares. And the vector is non-zero, correct? Remember, this is for all non-zero vectors. Therefore, at least one of the Ci's is non-zero, and therefore this is strictly greater than zero. In the semi-definite case, I just have inequality everywhere, because all the lambda i's are still known to be not negative. So, I'll say respectively greater than or equal to 0. So that is the so what about the reverse direction? What do I do? I'm given the property that X transpose AX is greater than 0 for all non-zero vectors. So this is easier. It's given for all non-zero vectors. So what do I do? Use the given thing X transpose AX greater than 0 for X equal to
an eigenvector with some eigenvalue lambda.
So yeah. And then what do I get? Then X transpose AX is simply equal to Vi transpose A Vi, which is Vi transpose times lambda I Vi, which is just lambda. And I know that this is given to be greater than 0. So this shows, so this is the easier direction. All right. And for negative definiteness, negative semi-definiteness, it's all exactly the same. All right. So let's also remark something here. There is a connection between positive definiteness and the determinant of a matrix. simply because the determinant is the product of eigenvalues. So if I have a positive definite matrix, then the determinant is going to be
Positive.
positive. And if the matrix is negative definite, then the determinant is going to be, is it necessarily negative?
Depends on the order.
Right. So because when I multiply those, I'm going to multiply n negative numbers. So it's going to have the parity of n. So let's write this down. Determinant of positive definite matrix is greater than 0, and determinant of negative definite matrix not is, has sign minus 1 to be. All right. And also here's an exercise which may, for n equal to 2, okay, let's just do this. For n equal to 2, I have the matrix A is going to be of the type, let us say A, B, and then BC, correct? It's a symmetric matrix. So the question is, can I have a criterion in just in terms of the entries, saying that allowing me to detect whether A is positive definite or not? And the answer is yes. So let's do this. There are some things. If A is positive definite, then certainly the following things are going to be true, right? Determinant of A, which is equal to AC minus B square. What do I know about this? This has to be greater than 0. Okay, so just on the strength of this condition, what do I know about the signs of A and C? I'm subtracting a square, or rather AC is supposed to be greater than a square. Therefore, AC itself has to be positive. And therefore, A and C have to be either both positive or both negative. Okay, but in fact, let's do one more thing. The positivity of the determinant has to be true regardless of whether A is positive definite or negative definite in either of these cases, right? So, or negative definite. In both of these cases, the determinant has to be greater than 0. However, notice one thing. I can express this entry small a in terms of just the following, right? Okay, so 1 0 a 1 0. What is that?
So small a.
That's small a, and likewise small c will be the other entry, right? So this is 0 1 a 0 1 c. Okay. So depending on whether the matrix is positive definite or negative definite, the entry small a has and small c have to be either both positive or both negative. Correct? So both greater than 0 if a is positive definite, if a is negative definite. So the exercise is to check if the converse is true. That is, if all of these conditions are met, then can we say that a is so converse? And the answer is yes, the converse is true. So check. This is going to be important for us. However, so what we are now done with, we are now done with the linear algebra. Any questions so far? Very well. Now let's go to calculus. But just one observation. Observe. So preliminary observation. It's just a remark really. Suppose everything is a real valued function, remember? So let's suppose there is a real valued function g. Suppose this limit exists. It's a very simple remark. Suppose I tell you that there are points x that are arbitrarily close to x naught, such that the value of g of x at those points is greater than 0. In other words, I can find a sequence of points x1, x2, xn all convergent to x naught, such that for each one of xi's, the value of g is greater than 0. Then what can you say about the limit? Remember, it is already given to me to exist.
Is greater than or equal to 0.
Exactly. So let me just say this in words. So if very simple thing. So this arbitrarily closed points having value of g greater than 0, I'll just write it precisely. If for all epsilon greater than 0, there exists x such that it's at distance less than epsilon, and I should also say, and g of x is greater than 0, then okay, good. So with this behind us, let us sort of state the result. So recall definitions. One, what is a critical point of a function?
Points where total derivative vanishes.
Correct. And in case of multivariable functions, vanishes means the total derivative vanishes. It's the zero matrix. Okay. Yeah. And in that case, so let me just say that we will just use this definition for C1 functions. So for a C1 function, f critical point is a such that a is equal to 0, and the second one is the Hessian of a C2 function f at a, which is hf of a is equal to the matrix, of its second partial derivative. So let me just say del f, del 2f by del xi, del xj, this matrix I and j going from 1 to n. So I have already taken a C2 function. So what do I know about this matrix?
It's symmetric.
It's symmetric. Right? So this means that this is symmetric. So third one. So this is the new clue part. For a critical point A. No, started wrong. Critical point A is called non-degenerate if HF is in particular if this Hessian is non-singular, that is to say that if the critical point is non-degenerate, then what can I say about the eigenvalues of this matrix? Remember, they're all real numbers.
They're all non-zero.
They're all non-zero. So if this matrix is positive semi-definite, and if it is given to be a non-degenerate critical point, then I know that it's automatically positive definite. And likewise, if all of them are less than or equal to 0, then I know that they all have to be strictly less than 0 if I'm given that the determinant is non-zero. So with this out of the way, let's state the results. So I'm going to state the results for n equal to 1 case, and we will even prove them. And then we will see that the proofs really generalize in a natural way with the correct hypothesis. They just generalize to the multivariable situation. So now claims. Claims. So as usual, I have a function from u to Rn. So u is, a real valued function open in R for now. And then later on, I will change R to, or let me just say R1. Later that 1 will change to N. So suppose F has a local max or min at A. Then we have the familiar claims. If F prime of A exists, then F prime to 0. A is a critical point. So so this should be familiar from the first semester. How does the proof go? Just so we know it. Does the derivative need to, does the function need to be does the function need to have derivative in a neighborhood of A for this to work?
No, sir,
I don't believe so.
Come on. This should not be difficult. Is it correct as it is stated, or do I need to have derivative in a neighborhood of A?
So we require to on your teams.
Sorry, I missed that. Can you say that again, please?
So we need the derivative on your team.
Okay, all right. So how does the proof go?
So like we take f of a plus h minus f of a divided by h. Like
So f of A plus h minus f of A.
yes, so this will be always like positive or negative depending on whether it's
Right. So let's just take so suppose A is a maximum. So let's take the case of local maximum. So suppose that A is a maximum. A is a maximum is of course a poor language. Suppose we have a maximum at A. So sorry, while am I writing, just tell me the proof. So if I have a maximum at A, then what happens?
So like then f of a plus h minus f of a will always be negative in some neighborhood, and so hence f of a plus h minus f of a divided by h will be negative in when h is greater than 0 and positive if h is smaller than 0.
And therefore the limit of this quantity, because when you consider one side, has to be positive, has to be non-positive, and the other side it has to be non-negative, and the limit is given to exist, so it must be 0. So if I have a max at e, then f of e plus h minus f of a is okay, so f of a plus h is greater than or equal to 0 for h greater than 0 and less than or equal to 0 for h for sufficiently small these imply respectively that f prime of a must be. So the first one is saying that when I divide by a positive h, correct, and oh sorry, what did I write down? That's just wrong, no? So how do I make this right? Of course, both of these are, so there are several mistakes over here. So help me correct
So
them.
for the first one, the inequality will be reversed, I guess. And we need to
No,
divide by h, right?
right. So I need to divide by h, otherwise the inequalities otherwise are going to be the same. And let us say I want to stick with my first one, that f of a plus h minus f of a is greater than 0. That means that I have a minimum, correct?
Oh, sorry.
And right, so sorry, making multiple mistakes here. And this one would also be the same, correct? Whether h is greater than 0 or less than 0 doesn't really matter. However, to rescue myself, what I will do is I will keep the signs the same, but I will divide them by h. Sorry for this mess. Correct? Because both the numerators are greater than or equal to 0 in a sufficiently small neighborhood, just by the definition of a being a minimum. And so if I divide this inequality by a positive number, it will be preserved. If I divide it by a negative number, it will reverse. So if I now take the limit on both, then by the virtue of the first one, etc. So this is all right. So the question now, so the reason to go through this proof is, does this fact sort of go in a straightforward way if I replace 1 by n? So if I do this for Rn, then how does the so this is the proof now for n equal to 1. So what is the proof for larger n? I simply build on top of this proof. So what do I say? If I look in any direction, use n equal to 1 case for every direction. For f restricted to, let us say, a plus t times v, for t in some open interval. right? I mean, such an open interval has to exist because A is there is a neighborhood around A. So I will be able to travel in, if I fix any direction, let's say a unit direction, I will be able to travel some distance in both directions. So I've just set a parameterized line over there, and I'm now going to apply the result to the function when I pull it back by means of this parameterized line to an interval in R, and then I apply the same result. So use this case. So to conclude what? So if I do this, what do I get to conclude? What happens when I do this and calculate the derivative of the resulting one variable function? What is the quantity I get?
Directional derivatives.
Exactly. So I get the d sub v of f at equal to 0 for all directions. But now remember that f prime of A is supposed to be is given to exist. So that is the first thing. It exists. Therefore, it exists as an operator, and I can calculate its values on any vector if I know these on a basis. But I'm given that they exist for all v. I already calculated that it is 0 for all v, so it's the 0. So f prime of A is equal to 0 operator. 0. Okay, so this was straightforward. Now, the next part. Suppose A is a critical point. So now, so I'm still operating under the assumption that f has a local maximum or minimum at A, right? So that suppose is still there. So now let us say in addition, suppose in addition that f double prime of A exists. Then can I use the double derivative to say, then can I say anything about the double derivative based on the fact that the given thing is a maximum or a minimum? So what can we say? Suppose I know that the given point is a maximum, local maximum. Then if f has local maximum at A, in fact, the first then is not required. Then what can I say about the double derivative?
Similarly, if we consider the directions
Right.
and use the n equal to 1 case, then we get that in a basis, I mean, for a set of basis vectors, this will be positive.
Right.
Negative. Sorry.
Right. Okay. So we will go to the proof, but let's just say for one variable situation. So what do we know? So for n equal to 1. So for now, so for n equal to 1. And then we will see how to generalize it. So if n equal to 1, then what do we know? If f has local max, respectively local min, then f double prime of A. What do I know? Do I know any statement like this?
For a local maximum, it should be non-positive, and for a local minimum, it should be non-negative.
So if I have a local maximum, then it looks like minus of x square, let's say. So in this case, it is greater than or equal to 0, and in this case, it is less than or equal to 0. So I have to suitably modify these when I go to the multivariable situation. But can we prove this? because then later on I want to do exactly what we did before, which is to apply this in every direction to conclude something or the other. And then life will become a bit interesting because this is where some linear algebra will come into play. But anyway, can we prove this first? So what do we do? Surely this must have been done in the first semester, right?
Sir, f dash A is continuous at A.
Right. F
F
prime
dash
of
of X. Yeah.
right. And its value is 0, but so what? So what is so notice. So what is so proof? What is f double prime of A? So this is n equal to 1, right? We are in n equal to 1 case. So what is f double prime of A? This is limit as h approaches 0 of
F dash of X plus A plus X minus F dash of A by X.
by h. But that is just 0 because I'm operating at a critical point. Remember, we already said that since I was given a local maximum or minimum, the second derivative exists at this critical point. So of course the first derivative exists, and we proved that it is 0. So this is gone. So f prime of A plus h divided by h, limit as h approaches 0. So you see, it's the, if I show that the value, so now I go back to my observation. Remember the observation that we had. So what is going to play the role of g of x is this function f prime. So do we know anything or the other, anything at all about the values of f prime? Does f prime have to exist away from A at other points? Yes, of course, because the double derivative exists. The double derivative is the derivative of the derivative. In order to calculate the derivative of a function, this function has to be defined in a neighborhood. So f prime of A plus h does exist for small a, for small values of h. And now what can I say about it?
There will be, if we have a local maximum, there will be a sequence which is decreasing. There will be a sequence of points where f dash is strictly positive and decreasing. And we can get this by mean value theorem, I think.
Correct, exactly. So it's a mean value theorem is required. So how do we use the mean value theorem? See, we are used, so the fact that let's say I have a maximum, right? Or let's say minimum, because that I used, that's what I used before. If f has a minimum at AB, then what do I know? That for small h, for h less than delta, greater than 0, I have that f of A plus h is greater than f of A. So what does mean value theorem tell me when I apply it to the window from A to A plus h? There is, let's say, k between 0 and h such that f of A plus h minus f of A, which is greater than 0, is and in fact let us say divided by h is equal to f prime of k. So what does this say? Remember, the numerator is in this window is always a positive quantity or non-negative quantity. And so above also we will just say non. Suppose this observation, it doesn't really matter. So the numerator in this window, so for every such h, the numerator is going to be greater than or equal to 0. And what about the denominator? When h is positive, the denominator is going to be positive, and when h is negative, the denominator will be negative. So what will happen? For every point to the right of a, so here is the thing. So this is a, this is a plus h, and this is a plus k. And here is another case where a plus h, and I get the corresponding a plus k. So what do I get? Here, we must get f prime of, f prime of a, that is small a plus k. I should just have taken small a to be 0 to simplify matters. A plus k. So here f prime of a plus k, what must be the sign? Okay, all right. So help me over here. When h is positive, this quantity is positive. So here I have f prime greater than 0. And here f prime is less than 0. But actually, you see, just one of them is enough. Right. And just to make things consistent, let me change this h to. So what happens? In the limit above, the quantity that I have, f prime of a plus k, forget the fact I'm dividing by k. The quantity up top is going to be, when k is positive, the quantity up top for infinitely many values of k. I mean, for every small h, I can get a small k, correct? The quantity up top is going to be greater than or equal to 0. And I'm dividing it by a positive quantity. Therefore, the ratio will be greater than or equal to 0 for infinitely many values of k. As a result, when I'm taking the limit of such values, the limit has to be greater than or equal to 0. I can see it also on the negative side, because on the negative side, here, the quantity in the numerator is less than or equal to 0, but quantity in the denominator. So either one of these is. As a result, using the observation, limit as k approaches 0 of minus k divided by k, which is equal to f double prime of k, must be greater than or equal to 0 for a min. And similarly, the observation is for the max. So very good. So this is for any n greater than 1. N is equal to 1. What does this argument give me when n is greater than 1? So I can use the exact same trick like before, which is restrict everything to one direction vector. So what happens? So for n greater than 1, what does this argument give? When we apply to each f restricted to whatever we had, so a plus. What do we get?
All of these have to be non-positive or non-negative, depending.
Right. So let us just so let us just say that we are working with local minimum, right? For because for the local maximum you just apply the same result to minus of f. So there is nothing over there. So for definiteness, let's suppose that I have a local minimum. Then what is it that I get to be always non-negative?
All directional derivatives.
All the directional double derivatives. You see.
Yes, sir. Yeah.
So what are those directional double derivatives? That is interesting, correct? So I get that all d sub v square of f at a are greater than or equal to 0. So we should understand what this means. I am taking the directional derivative of f, but not only at a, but in a neighborhood of a. And that is now again another real valued function because I'm calculating it at every point in the neighborhood. And now I'm taking the directional derivative of that function once again. So let us now go back and yeah, all right. So in this case, okay, we will come to the hypothesis whether we want to put additional hypothesis here in the multivariable situation. So what do I know about what do I know in particular all in fact, let me not write that down. Let me just say it. In particular, if I calculate all of del by del xi, del by del xj of f at a, then all of those entries are sorry, no, that came out bad. So if I calculate all of del square by del xi square of f at a, all of those entries are greater than or equal to 0. But this is saying a lot more, right? This is saying that so this is interesting. So notice what this is. Writing. So let's write this in terms of the Hessian. The Hessian HF at A, and let's just call it H. So what do I know about, so let us say, suppose V is equal to summation, let's say, xi ei, right? Then what is dV of f at A?
F dash of AV.
In fact, let's not write down at A. Let's just write this down. Yeah. So, I mean, if you want, you can think, in fact, let's do this. Okay. But this is going to hold in a neighborhood, right? So remember that V is a linear combination. The function is differentiable. It is double differentiable at that point. So it's differentiable in a neighborhood. Total derivative exists means every directional derivative is going to be a linear combination of the partial derivatives with the same weights. So what is the formula for this? So this is summation. In fact, let's not use xi because xi are my variables. So let us say vi. Oh, this is bad because earlier my vi were CIEI. Okay, so tell me what happens now. This is precisely going to be summation CI times DI of F at A. But this is going to be true at every point wherever the total derivative exists. So this is going to be true in a neighborhood. So I'm simply going to drop the a over. And what happens in a neighborhood of A? And so what happens when I calculate the second derivative, partial derivative? What does that give? Hello, what does this give me? Now I have to take the summation V as summation Cj Ej once again and apply the same result what I applied earlier for the function f when I took the directional derivative. I'd have to apply the same function to each one of the partial derivative functions, that is to each dif. So now I will get a double summation, and what will that be? I comma j Cj Ci dj di of f, and I will calculate this. In other words, what is this in terms of the Hessian? Therefore, d sub v square of f at A is what? I'm going to write the Hessian matrix H, and then what do I do?
So C transpose on one side and C on the other
And C
side.
on the other side, right?
Yes.
So exactly. So this is, so let me just write this down. So this is going to be C1 up to Cn and C1 up to Cn. So this is the vector. Okay. So but that was the vector v. So I've written it in the column notation. So this is exactly v transpose hv. This is where now the positive definiteness or negative definiteness comes into play. So what is the upshot? We know that this is the case.
Hello, sir.
Yes.
Sir, could you explain how did you get the D2VFA once again? I mean the
Right.
double summation.
Correct. So let us look at that. Look at this one first. This one gave me this. This is okay, right?
Yes, sir.
Now I'm going to apply the same result to the functions DIF.
Okay, sir. Yes, sir. Now
Right.
I get it. Yes.
So perhaps I will just write this down. Oops. So this is equal to dv of summation ci dif over I, and I apply the same formula. That's why I picked up an extra cj in front of ci and an extra, and now all the dj's apply to di. Okay, so what is the upshot? The upshot is that, so thus the result is that, let us state the result. For n equal to 1, if f has local maximum, then f double, the sign of the number f double prime is, it is less than or equal to 0, and respectively for minimum it is greater than or equal to 0. What did we find out? So upshot. So the upshot. We proved that if f is a C2 function at A, then by virtue of by virtue of 0, what I found out was that this V transpose than or equal. Let's go back and look at, but if f is now a C2 function at P, then what do I know about the Hessian? So H is a symmetric matrix such that what happens? Let's go back to our linear algebra thing. If I have a symmetric matrix, then this quantity always being greater than or equal to 0 was equivalent to that matrix being uh, positive definite or positive semi-definite, depending on whether it is strictly greater than 0 or weakly greater than 0. So what have I concluded?
H is positive semi-definite.
Exactly. H is positive semi-definite. If F is a, so H is, we proved that. H is positive. But now if it was given to me that the critical point is non-degenerate, that is to say that the Hessian is non-singular, then I can simply drop the semi and sorry, just 1 second. If f is a C2 function at a local minimum, without that this makes no sense, then H is positive semi-definite. If in addition H is given to be non-singular, A is as a non-degenerate critical point at the local minimum. Then H is positive definite. Okay. So what we want to do now is we want to prove a converse. By the way, so I should say, so what is the analog over here? If n is greater than 1, then these things stay exactly the same. So I'll just say for n greater than n greater than 1, greater than or equal to 2. Assuming addition that f is C2. Then instead of this, what do we get? F H is H is what? Negative semi-definite, and here I get H is positive semi-definite. Okay, so now what we want to do is to prove a converse, which was our goal last time. See, often in practice, what we want is to find the maximum or the minimum, right? So, so just like the one variable calculus, what we do is we find the critical points, and then we would like to test, can I decide whether this is a maximum, local maximum, or a local minimum? So I want to go in the other direction. And the result is what we stated yesterday. Namely, I can prove the converse to this, which is to say I have a critical point where I assume that the Hessian is non-singular. Then I simply look at whether the Hessian is positive definite or negative definite or neither one of them. I do not have to say, I do not have to worry about any eigenvalue being 0 because I have assumed that H is non-singular. And so there is this sort of new situation. Okay, so then what happens? If the Hessian is positive definite, then we want to show that the function has a local minimum. If the Hessian is negative definite, then we want to show that the function has a local maximum. And if it is neither, then it is interesting. That means that I'm going to have a positive, I'm going to have a positive eigenvalue as well as a negative eigenvalue. So this is a very nice geometric interpretation. What that means is that if I take those principal directions, then what happens? Along one direction, the directional derivative is going to be negative. The double directional derivative at this critical point is going to be negative. Whereas in another direction, this directional double derivative is going to be positive. So what do we call such points?
Inflection points.
Yeah, so this is actually interesting. You should think of a mountain pass. If I'm going from one valley to another, that is one direction that you're going in, then you have to climb up and go down. So at the top of the pass, for your path, you have a local maximum. But imagine that you were going instead from one peak, then down to this in between pass point, and then to the other peak. Then in that direction, you have a minimum. So those will correspond to the principal directions in which your Hessian has an eigenvalue. So this is a new phenomenon that one does not have in one variable situation. So this is going to be our goal for tomorrow, and so we will stop today.
Recording stopped.
Yeah, so I'm happy to go on. I mean, somehow this went slower than I wanted. I thought we would be able to finish the theorem. Maybe let me just state it, and then if you want, we can discuss this. So play. So this is a converse. Suppose f is C3 function on U. So I'm given a critical point. Then if f double prime of A if I think of this as a matrix, so the real valued function, so on U in I know that f has a local minimum at A, and respectively, what is going to be the condition for n greater than h is positive definite. And in exactly the same way, if f double prime of A is less than 0, respectively, h is negative definite, then f has a local max. Okay, so I'm going to assign this as an exercise because everything that is required for this is now done. There is only one extra idea, because you see in n equal to 1 case we did this proof in the last class. How was it done?
We use Taylor's theorem up to
Exactly.
yeah.
We used Taylor's theorem approximation up to degree 2, and then we had a degree 3 error term which we were able to use, correct? All right, so we do exactly the same thing. over here. We have a C3 function, so we have proved Taylor's theorem. The only thing is, how is the positive or negative definiteness going to come? Well, it's sort of just written out, no, for us. So let's go to the, yeah. So this was the previous class, and so 1 second. So right. So you see this thing over here. So we want to show that f of a, the value of f of a is whatever local maximum or minimum. What about the second term? What happens to that? We are at a critical point. So the gradient is
0.
0, right? I mean, gradient f prime of a, it's really the same thing. One is transpose of the other. So that term is 0. That remainder term, we know that when I divide by the norm of, it's of the order of norm h cube, correct? Bounded by some constant times norm of h the whole cube. So if I divide it by the norm of h the whole square, then that term goes to 0 as h approaches 0. So I have some bound on that. And what is this second term? I mean, what is this third term? That is precisely this H transpose, what we called V transpose. I mean, we denoted it by a vector V. V transpose times the Hessian times V. But we know exactly what that term does when H is positive definite. We know that no matter what H you take, that quantity is always positive. I mean, for non-zero H. So I do the proof in exactly the same way that I did for the one variable piece. That half of f double prime of a. Instead of that, I have Hessian, but when I'm evaluating the function, really that Hessian I have taken multiplication on one side by some vector v, and on the other side by the transpose of the same vector v. I know that such a term is positive. Always. So am I done with the proof? Not quite, you see, because the way we did it over here was that this term was a certain fixed positive number. So I just made sure that my h was small enough such that RH divided by h square could never beat this fixed number. And so within that neighborhood, this term dominated. I have a problem with this approach I have a problem because in the situation that I have, okay. So where do I have this? V transpose HV. Can I say that it is always greater than a certain fixed number, no matter what V is? No, you see, because V could be any small, V could be a very small vector. But the point is, what I want to do is I want to divide by the norm of V the whole square and get a bound on that. And that is possible. So what do? I get a bound on this function, a lower bound on this function when the norm of V is 1. And it is possible because what?
Positive definiteness, the fact that the Hessian is continuous, and the compactness of the open.
Exactly.
That ball.
Exactly. So you see, when I'm basically dividing this by the norm of V square, effectively what I have to do is I have to get a bound on this for vectors of norm 1, but that's a compact set. And here this function, if I think of this as a function on V for this Hessian, which remember Hessian is at A, so it's just a square matrix of real numbers, constant real numbers. So this quantity is clearly a continuous function in the entries of V. It's going to be a quadratic function. So it's certainly continuous. So on the unit sphere, it is going to take a maximum and a minimum value. The point is that for all non-zero vectors, it is strictly greater than 0. So this minimum value on the unit sphere is going to be strictly greater than 0. That is the value you beat. That is the value that you ensure that you do not beat by your error term. And that just gives you the result on the plot. So we will do this properly in the next class. But the point that I wanted to emphasize in today's lecture is that once you set up this linear algebra, which really is just one thing, that what are positive definite and negative definite matrices. And all that you require is that you can diagonalize a symmetric matrix by means of an orthogonal matrix. That's all that is required. Once you have that, then the development is entirely parallel to the one variable development, nothing much more. Of course, we are building on top of what we did earlier, which is the Taylor's theorem, and before that, the symmetry of the partial derivatives for C2 functions. All of that is required. But once you have that under the belt, it really is parallel to the one variable development. Okay, so please try to sort of see this and fix it in your mind in such a way that it doesn't take up a lot of space. Nothing much is happening after all the scaffolding that we have built. Nothing much is happening over here. So try to do this proof, fix it in your mind, and you can try to work out some examples, but we will do them in class also. Okay, so are there any questions or anything else?
Sir, like you said something about like if you go in one direction, it will increase, and if you go in another direction, that function will decrease. Can you repeat that, sir?
Okay, so this was for the for the here, no, I think here. Was it here?
Just before you stopped recording.
So now I don't recall.
I think it was what you said.
Okay. You're talking about the saddle point. Okay.
Yeah.
All right. So picture a horse's saddle, or picture a mountain pass, or you can picture a Pringle chip if you have sort of ever seen one. It's difficult for me to draw this. Hopefully I can get some software going so I can show this. Okay, so here you see, suppose this is the situation. Okay. So imagine that this is something that has it's not a one variable thing. So it has some girth. So these are like contour lines. So, right? So you're thinking of this as a function of two variables, real valued function of two variables. So here is x and here is y and here is z. So z is this is y, z is equal to f of xy. That is the graph. So the way this is happening is that if I take this curve, I'm going from this side of the mountain, or this side of this sort of, well, not mountain, this valley to the other side. So in other words, I'm going in what direction? I'm going in y direction. So let's say that's the y direction. And let us say this is the x direction. So this is the curve in the x direction at that point, and then they're meeting at that mountain. So the way I have drawn it, the eigenvectors of the Hessian, they are just in the x and y direction, respectively. So what will I get? I will get del f2, sorry, what am I writing? Del 2f by x2. Remember when we said du square of f, right? Or dv square of f. So what is happening now is in the x direction. So what can you say about the value of this function? Look at the blue curve at a.
It's positive.
Correct. And if I do it in the other direction, so this is greater than 0. Well, I mean, it need not be greater than 0, right? Remember, there is the thing that the double derivative test can fail. But the point is, if this double derivative is greater than 0, then I know that in that direction, at the critical point, I have a local minimum. And likewise, I can write that del 2f by del y2 is less than 0. Or maybe I will just say this is greater than, and now this is perfectly fine. If I start with this picture, then I know that about the double derivatives. So you see, this kind of phenomenon you just do not encounter in one variable case.
Yes, sir. Since we have only one direction.
So, I mean, if you want, by the way, I'm saying n equal to 1 versus n greater than 1. It is not like those two situations are different. It is just that the Hessian, in case of n equal to 1, is just a single number. It's a 1 by 1 matrix.
Okay, sir.
So the linear algebra just doesn't come into play. You just see whether that number is positive or negative. But the nice thing is that by means of using this symmetry, there is a notion of and facts about eigenvalues of symmetric matrices. There is an analog in which, there is an analog where there is a precise generalization of this. You see positive definiteness or negative definiteness of this matrix. Anyway, I will do this again in class when we'll also do examples. Okay, so anything else?
So are there any functions which just real functions?
I'm sorry, say that again. What about real functions?
So I was asking if there are any functions which are differentiable everywhere, but continuously differentiable nowhere.
Okay. So let's go back to one variable situation. Can we do such a thing? Differentiable everywhere, but the derivative is not continuous anywhere. We can certainly do that because there are functions that are continuous everywhere, but differentiable nowhere. So what do I do to such a function?
Take the integral.
Yeah, so take the Riemann integral of this. Sorry, does that no, one second. One second. Does that work? No. Sorry, one second. What? No. No. So no, sorry. That doesn't make sense. No? So what you want? Okay, so let me. Sorry, I spoke hastily. So you want? Okay, so let's just see. So you want a function that is differentiable everywhere, but the derivative is not continuous anywhere. Right? Was that the question?
Yes.
Okay, so always good to think before one speaks. So that doesn't help, no? Because what I said is right, but that says nothing about the given situation. The answer should be yes, but can we think about this?
Like, sir, if you have a function that isn't continuous anywhere, but still Riemann integrable.
No, okay. So can we
Just like Dirichlet's function.
sorry, say that again.
Dirichlet's function.
Yeah, so what is that?
It's 1 for rationals, I think, or 0 for
Right.
rational.
Okay. So okay, so this is difficult already for me.
That would just.
But I mean, is it Riemann integrable?
It's not, I think, and I think there is a characterization that a function is Riemann integrable if and only if it is continuous everywhere except on a small
measure
set.
zero
A
set
measure
or
zero
something.
set, yeah.
Yeah. So so I mean, derivatives of the functions. I don't see why it can be. See, if you want to use the fundamental theorem of calculus, then I mean, I know that it is there for Riemann integral. So okay, so how about just if we just go to stack exchange? Let's see. Always a trusty first stop. Right. Okay. It's differential. Okay. Okay. So there are various things. So of course, okay. There is something to. See, there are some things that I already found something on Stack Exchange. So the basic example to keep in mind, forget discontinuous everywhere. Okay. We have the following theorem in real analysis. If a function is differentiable everywhere, then the set of points where f prime is continuous is non-empty. In fact, it's a dense G delta subset. A G delta subset is intersection of countable collection of open subsets. Ouch. Okay. So you need the bare category theorem for this. Okay. So yeah, there is a bunch of. Okay. So the answer, so what I said is false. I'll just. Here. I'm just going to put this in chat for whoever is interested. Okay, so there is something by Ram. Okay. All right, so okay, so do I understand what is? Sorry, so 1 second. I think I wanted to send this to him. 0 of x is irrational, and 1 by b is continuous almost everywhere and Riemann integrable. I sort of don't see that.
I mean, sir, it's continuous like almost everywhere because we've defined it as 0 for all irrational numbers, and the Riemann integrability, like if you
Right.
crunch it out, I mean, you get that.
Right. No, okay, sorry. So I mixed up the rational and irrational. So this does not violate. But you see, everywhere is not possible because now the discontinuities of this in some ways it's also a small set. It's countable.
Yes, sir. Yeah.
Okay, so the link that I sent you, I'll just read it out. So this is nice. A set E is the set of discontinuities of some derivative if and only if it is a meager F sigma subset of R. F sigma subset is just a union of a countable collection of closed subsets. But it's supposed to be meager. So what is a meager set? Yeah, so there are various things. Of course, the first thing, the one that everyone should know, is the type of thing that you want to keep in mind is this function, no, the x square sine 1 over x. But of course, that gives a problem only at one point. Yeah, so basic example. All right, next. Right, exactly. So what seems to be happening is that you take this basic function and then you use that to create more and more discontinuities for the derivative. Yeah, you scale the functions and you add them. Okay, anyway, I think I cannot say anything better than these guys have said. So I think you should just take a look at the answers.
But so based on at least the answer, it just says that there are uncountably many like discontinued.
Yes.
Right. That's what they're trying to create, but it's not something that is everywhere differentiable, but
right.
continuously differentiable.
But it is still possible to create a discontinuous function. It is still possible to create a function whose derivative is discontinuous on a set of positive measure. Anyway, so this is
I've never heard of the fat Cantor set before.
Yeah, there is something called fat Cantor set. Nor I. All this is way beyond my competence. But fantastic stuff. So I think it's something to read. All right. So I think we can all, whoever is interested, can take this as homework to read and understand this. All right. So is there anything else? You see, it just, I just blindly, it's like, what they say. Fools rush in where angels fear to tread. So when you asked the question, I just blithely said, yes, there should be such a function. But you see, I just fell flat on my face. All right, so if there is nothing else, then we will stop. We will next go, by the way, we will next finish this maxima minima thing. Then we will have constrained optimization. So Lagrange multipliers. For this, we will have to look at other references. By the way, even this local maxima, local minima, if you look in Rudin's book, he gives this as an exercise, which is really absurd. It's the last exercise in the chapter, I think number 31 or something like that. He doesn't tell you the answer. But it's a standard topic, which is there in many calculus textbooks. So after this, we'll do Lagrange multipliers. And once we are done with that, then you see that sort of trajectory to generalize differential calculus and its theorems, that is sort of complete in its way. Then we can go and do the really fun stuff, which is inverse function theorem and implicit function theorem. I think we will have some time left in May. We should be able to do all of this in this month. We should be able to finish. Maybe even a bit earlier, and then in May we can sort of see if people want. Then we can do some of the things that came up during the course, but which we did not take up. There are a number of such possibilities. Of course, several of these you will do in next courses. You will do in topology, you will do in analysis 3 or elsewhere. But we could perhaps try to do something. So if you have some wish list, then you can let me know that this is the direction that you would like to see. Okay, so let's stop and then we will continue on Friday.
Thank you, sir.